Okay, solid solution strengthening. This is a little bit more easy to wrap your head around than some of the things we're talking about with grain boundary interactions. But let's hear it one more time. Dislocations interacting with other obstacles, gives rise to strengthening. Here we're talking about the interaction of dislocations with solute atoms in solution, right? So the stress field of a dislocation is long range, right? And solute atoms you can imagine that a solute atom either being bigger or smaller than the atom that it is replacing is going to also have a local stress field around it, right? And these two long-range elastic stress fields will interact with each other, right? For the most part, we're only going to consider the short-range interactions as kind of a first approximation of the overview. First order analysis, we'll say. But it gets us most of the way there. And you'll see it's pretty good. So we're only going to consider atoms that are lying pretty close to the glide plane. So here's our picture. Here we have a edge dislocation on the slip plane. And let's think about the stress field above and below this dislocation. Here we've got this extra half plane of atoms, right? So these atoms are squished together, right? So they are seeing a compressive stress. Down here, these atoms are pulled apart, so they're seeing a tensile stress. Now imagine here we have, right above the slip plane, we have a solute atom that's smaller than the atoms that it's replacing, right? So this interaction energy is going to be negative, right? As the dislocation moves here, this reduced volume smaller volume is going to reduce the compressive stresses that are above here, right? So this dislocation would be attracted to the solute atom. Now imagine if this atom were now down here, just below the slip plane, right? That would have a positive energy and would tend to repel the dislocation, right? And the opposite would be true. If I had a big dislocation, a big solute atom up here, it's going to repel this dislocation. And the big solute atom down here is going to attract this dislocation. Okay? And the stress fields of these substitutional solid atoms, right, are what we call a spherically symmetric. There's a spherically symmetric stress strain field around them. So we call these a weak obstacle, or a spherical distortion of the lattice. All right, we'll talk about tetragonal distortions, or asymmetric distortions, in just a little bit. But as long as there's no vacancies or anything here, we can think of this as a perfectly spherical isotropic stress field. Okay. So now, when this dislocation started moving, this solute atom was far, far away, right? It could have, right, just as easily been one atomic plane up or one atomic plane down, right? So on average, the number of repulsive and attractive cases are going to be equal, right? This dislocation, as this dislocation moves along, it's going to see the same number of substitutional atoms just above the slip plane as just below the slip plane. All right? But the dislocation line is flexible, right? The line tension isn't all that great. So the dislocation does not have to stay in a straight line. It bends with a small energy penalty, right? And so a greater fraction of the dislocation line is going to be found at locations where negative interaction energy exists, right? Dislocation is going to bend around positive attraction energies and towards negative. So if we average over the total number of edge dislocations and go along the total length of them, right, the interaction energy between an edge dislocation and a solute atom is going to be negative, right, on average, right? Because the dislocation doesn't want to be near the positive ones, it wants to be near the negative ones. Okay. So this is for edge dislocations. For screw dislocations, the stress field is in a state of pure shear, right? So there is no size effect interaction for the screw dislocations. We don't there are other effects acting on a screw dislocation, but it doesn't. For a screw dislocation, doesn't care whether it's big or small, right? This pure distortion of the lattice doesn't affect a screw dislocation in the same way that it does an edge. There's some new calculations that show a small second order effect for screws, but we can ignore that for now. Okay, so I said that's the size effect for substitutional solution strengthening, and I said these are spherical distortions. We can have tetragonal distortions, such as a vacancy in an ionic crystal, right? Or interstitials in BCC. The carbon interstitial in iron leads to a tetragonal distortion because it's in a non-symmetric neighborhood. And the interaction with screw dislocations and tetragonal defects is very significant because this is a non-spherical distortion. Right, so you have shear distortions, and the shear distortions of the screw and the shear distortions of this magnify each other. We'll talk more about these, but these tetragonal distortions are considered hard distortions. Okay. So I just wanted to throw that in there. We'll come back to this concept in just a little bit. But this size effect, right? The fact that I have that my substitutional atom is a different size than the rest of the lattice around it has a strong effect on dislocations with edge character. Okay? So let's look a little bit more carefully about the magnitude of that. So we're going to define this epsilon b. This is not a strain, but it is a strain-like parameter. Right? So it's a dimensionless parameter that's going to relate the size of the solute atoms relative to the solvent. Right? So it just tells us how, and it's a relative parameter, so it's a strain-like. Right? You can think of it as a ratio of the size of the atoms. Okay, the lattice parameter. Oh, that should be parameter. For a binary alloy, it can be expressed as a fractional change of lattice parameter per unit concentration of solute atoms. Right. So this is the lattice spacing. Right. This is the change in lattice spacing with respect to concentration, right? And that we can define our E sub b in that way. Okay, so if we replace a solvent atom of radius r by a solute atom of radius r1 plus epsilon b, right? It's not hard to derive that the local change in volume has to be this, right? And so the interaction energy between the edge dislocation and the atom can be found by multiplying dV, the change in volume, by the trace, the hydrostatic component of the stress field, right, which is the trace of the stress divided by 3, right, around the edge dislocation. So if we do that, right, remember this is nothing but this strain-like parameter times the hydrostatic stress, right, we get a form that looks like this, right, where r is the distance between the dislocation core and the solute atom. Theta is the angle between the line connecting the core with the atom in the slip plane, right? So this has been generalized for an arbitrary geometry, right? And this is the energy of an edge dislocation due to the distortion of the lattice, right? And it's always negative. And for screw dislocations, it's always approximately 0, right? Again, because this is a spherically symmetric distortion, and the edge dislocation only has shear components for its screw. So if you work through it, you'll see that it can't possibly interact. Now there's that's the first interaction. That's the size interaction. That comes from simply replacing the solute atoms with larger, smaller solvent atoms. There's another interaction that comes from the modulus, right? The bonding energy of the solvent atom. Now you can imagine, right, in a perfect lattice, all the atoms have the same bonding strength. They all see the same local stiffness. If I replace a solvent atom in there, it's going to have a different bonding energy, right? So it could be a stiffer or a weaker bond, right? A stiffer or more compliant bond. And so that's going to affect the energy of the dislocation as it goes through. Okay? So the energy of a dislocation is going to be proportional to the shear modulus, right? A substitutional atom that is more compliant or has a smaller g is going to attract that dislocation. The dislocation has less energy when it's near that solvent atom than when it's farther away. If the atom is stiffer, has a more stiffer bond, then the dislocation is going to be repulsed, right? The dislocation has more energy when it's near there. So size effect is always a negative interaction. If I have a compliant solute atom, it's also negative, and the effects combine constructively, right? So smaller, softer, smaller, more compliant atoms will give you a large strengthening effect, right? A stiff solute atom gives you a positive interaction, and so it combines destructively, right? So compliant solute atoms end up being hard obstacles. Diffuse solute atoms end up being weak obstacles, right? And the modulus effect does not depend whether the solute atom lies above or below the glide plane. Okay. So here's the warning in the reading. The language in Courtney is confusing, right? He uses hard atom to mean stiff and soft atom for compliant, right? Meaning that a hard atom is a weak obstacle and a soft atom is a hard obstacle, right? So that's why I switched it to compliant and stiff, right? So a compliant atom is a hard obstacle, makes sense. Whereas a soft atom is a hard obstacle. A little confusing. Okay. So the magnitude of this modulus effect. Okay. So again, we're going to define another parameter, dimensionless parameter, epsilon g, which represents the fractional change in shear modulus per unit of solute concentration, and analogously to the size, right? This is the fractional change with respect to concentration. And just for because it leads to a prettier final form, we're going to normalize this in this way. We're going to normalize it by 1 plus the magnitude of this, whether it's positive or negative. And we're not going through the derivation, but we have this is the effect for a screw dislocation, right? The R cubed dependence, and an edge dislocation is exactly the same, but it also has the Poisson's ratio, right? This is the Poisson's This is the Poisson's 1 minus the Poisson's ratio term that shows up in the stress field around the dislocations, right? And in homework, you'll play with these terms and see how they work out. Okay, so combined effects, right? So if you have a compliant atom, you get a additive effect. If you have a stiffer solute atom, that effects partially cancel each other out, and so you have less of a strengthening effect. Okay. So the shear stress to overcome the interaction, all right, tau is this max force divided by the Berger's vector, and the L prime, this is the equilibrium spacing, or the effective spacing, not equilibrium spacing. All right, and so for the max force is going to be GB squared. This is the critical angle as we bow around it. All right. So for weak obstacles, this is going to, this is going to be on the order of GB squared by 100. For hard obstacles, it's GB squared by 5. So basically, we end up with a factor of 20 difference between spherical, which is what we just talked about, and tetragonal. Right. So here we have the change in stress, right, for adding gold and copper. Right, you can see it's pretty weak. Right, but adding carbon in iron has a huge effect. Right, and it's because we have these tetragonal distortions, these non-spherical distortions. Right, gives a much larger interaction penalty than a substitutional solid solution. So anytime you can stick something in the interstitial, especially in BCC, right, you're going to have a much bigger point. Anytime you have a distortion of your lattice that is not symmetric, right, such as a vacancy in a ionic material, it's going to have a very large effect. Okay, and we'll come back for the last part on particle strength.